Hello and welcome. In this video, we're going to look at another type of improper integral called the type 2 improper integral. Figure 5 shows an example. In Figure 5, we're looking at the integral from 0 to 1 of 1 over the square root of x. So in this case, our interval is from 0 to 1, but notice that at x equals 0, we've got this vertical asymptote for 1 over the square root of x. Now, if you were to try to evaluate this integral, you might worry about the fact that the function is undefined there. I mean, what happens when you go to plug in x equals 0? Integrals like this, where you have an x value either at one of your endpoints, like in this case, the left side of our interval at that endpoint, the function was undefined, or if the function is undefined somewhere in the middle of your interval, then you'll have to consider that and evaluate it as an improper integral, a type 2 improper integral. So how do we do that? Well, just like the type 1 improper integrals, we're going to take that x value where there's a problem, which in this case is x equals 0, replace it with a letter like t, and then take the limit as t approaches that x value. So as t approaches 0 from the right in this case. So as t approaches 0. What that does is it takes these areas and makes them closer and closer and closer to the area that we're trying to look for, from 0 to 1 of 1 over x squared. So I guess just like in the last time, we would take the limit as t approaches 0, just like t went to infinity for the type 1 improper integrals. So here's what it will look like. If you have a function, which is your integrand, that's continuous on your interval from a to b, but discontinuous at a, so that's like the left side, kind of like in Figure 5. The a is like 0 in that case. Then to evaluate the integral from a to b of f of x dx, you will replace the a, which is where that discontinuity was, with t, and then take the limit as t approaches a from the right. If your discontinuity is on the right side of your interval, so if it's at b, then you can replace b with t, and then take the limit as t approaches b from the left side of the integral from a to t of f of x dx. And then if your function is discontinuous at c, where c is just some x value inside of your interval from a to b, then you can evaluate that integral by splitting your integral up into two separate integrals. One that goes from a to c, and then one that goes from c to b, and then add those two improper integrals up. Each one of those improper integrals is going to have to be evaluated as a limit, so like the first and the second one that we were talking about. So for each one, you replace the discontinuity c with some letter like t, and then let t approach c, either from the left or the right side, depending on how it's set up. We'll talk about that when we do our examples. So just like the type 1 improper integrals, we would say that if the limit in these cases are finite, we would say that the improper integral converges. And if the limit does not exist, the improper integral diverges. Example 4 asks, find the integral from 0 to 1 of 1 over 1 minus x dx. So where is the discontinuity? If you said x equals 1, that's correct. When x equals 1, the function is undefined and therefore discontinuous. And actually you can see it in Figure 7 as well. It graphs 1 over 1 minus x, and you can see that at x equals 1, that's where the vertical asymptote is, and that's where we have a Okay, so as a first step, we're going to replace that discontinuity with a t and let t approach that discontinuity. And you can see that we're approaching from the left side of 1 by looking at figure 7. So if you look at replacing 1 with a t, that t value is going to be some number that's inside of your original interval. So it's some value between 0 and 1 in this case. And so if you want to think about t as being some number between 0 and 1, t is going to have to approach 1 from the left side of 1, right? Because t, if 1 is on the right side, t is to the left of that because it's still inside your interval. So t is going to have to approach 1 from the left side. Now when you're not given a picture, what I'd recommend is just drawing or imagining your interval, so in this case from 0 to 1, putting t inside of that interval, and then wherever the discontinuity is, that'll tell you if you're approaching that discontinuity from the left or the right side. So like in this case, x equals 1 was where the discontinuity was. So here, t is going to have to approach 1, and it's doing it from the left side of 1. It's moving to the right, but it's on the left side of 1. Okay. So then we have the integral from 0 to t of 1 over 1 minus x dx. We'll find the antiderivative of 1 over 1 minus x, which should be negative ln absolute value of 1 minus x from 0 to t. Where's that negative coming from? Basically, it's coming from the chain rule, or a u substitution, you can think. So let u equal 1 minus x. The du will be negative dx. And that negative 1 coefficient in front of the dx, when you divide it over, gives you a negative in front of the du. So that's where that extra negative is coming from. Or you can think in reverse, it comes from the chain rule. If you took the derivative of ln of 1 minus x, that would be 1 over 1 minus x, but then times the derivative of 1 minus x, which is negative 1. So you need that extra negative to cancel off the negative 1 that multiplies out from the chain rule. So however you do it, mental u substitution or just thinking about the chain rule in reverse, that is okay, as long as it leads to the right place. Alright, so now we're going to have the limit as t approaches 1 from the left of negative ln absolute 1 minus t minus negative ln absolute 1 minus 0. Ln 1 minus 0 will be ln 1, which is 0. So don't need to worry about that. And then if we take the limit as t approaches 1 from the left of ln 1 minus t in absolute value, well, 1 from the left means we're a little bit smaller than 1, something like 0.9, 0.99, 0.999. So those numbers, when we do 1 minus those numbers, they're going to get closer and closer to 0 and are positive, although we have absolute value bars around the, that anyway, so it's going to become positive anyway. And those positive numbers getting close to 0 are being inputted into the natural log function. So if you think about what the natural log function looks like, and then think about, so here's the natural log function, I'll use t, and then think about the inputs getting close to 0 from the positive side, the outputs are falling down to negative infinity. So here we would get the negative of negative infinity, which is positive infinity. All right, there's the extra negative that's out in front. Ooh, you saw my taskbar. Oh well. Nothing incriminating there. So we have negative of negative infinity. All right, And so therefore, this area is like an infinite area, so we would say that this improper integral diverges. So diverges. Because it did not give us a finite number for the limit. Okay. So thank you for watching this video, and see you in the next one.